Hello, hello, hello. Welcome to my class, Industrial Electronics. So let's continue with this. Let's continue with a new topic. Okay, I will have a new topic. We're now in differential and instrumentation amplifiers. Okay, still okay. So this is what the differential amplifier looks like. Okay, so aside from having a feedback resistor, so you have negative feedback, okay, input resistances R1. We also have R2 and R3 here. Okay, so we have V out simply equal to V2 minus V1. So differential amplifier is like a combination of non-inverting. Okay, so let's have a review. So non-inverting, we have negative feedback input resistances, and take note of the input input voltage is just before the non-inverting input. So the equation is 1 plus RF over RI times V in. And the inverting, so again, we still have the negative feedback here, input resistances. And then the input voltage is, the application of input voltage is being applied here, okay? Before the RI, okay? So V out is negative RF over RI times V in. So how are we going to derive? So let's derive the equation V out is equal to V2 minus V1. Okay? So differential amplifier. So let's start. Okay. V out due to non-inverting. So let's start the analysis with V out due to non-inverting. Okay, so we have here. Okay, so if we're going to consider the non-inverting, okay, so it becomes like a non-inverting amplifier with an equation of 1 plus RF over R1 times B plus. Okay, so it's not V2, but rather B, the voltage here. Okay, so as you can see, okay, so we are pertaining to voltage just before the positive input. Okay, so we are referring to the B positive here, but they know that with respect to V2, okay, so you have a input voltage B2. Okay, how does R2 and R3 connected? So it appears that with respect to V2, R2 and R3 are connected in series. Okay, so it is in series. Okay, and therefore the V plus, so this point is B plus. So if we're going to use a VOM and then measure what is the voltage here, okay, so we'll actually top the positive probe here and the negative probe here. Okay, so essentially you are measuring the voltage across R3. Okay, you're essentially measuring the voltage across R3. So since R2 and R3 are connected in series with respect to V2, so we will use the voltage divider formula to determine the voltage across R3. Okay, so the voltage across R3, so V positive is actually the voltage across R3, which is equal to R3 over R3 plus R2 times V2. So that is our equation 2. So substitute the V positive of equation 2 to equation 1 as such. So this is the equation 1. So substitute the V positive with equation 2. Okay, so we have this. Okay, so this is our now equation number 3. Okay, so that is our V out due to non-inverting input. Okay, what is the V out due to inverting input? Okay, so due to inverting input, okay, so if we're going to consider V1, we have, okay, negative RF over R1 times V1. So it's just simply equal to negative RF over R1 times V1. Okay, so total V out is combination of V out due to non-inverting and V out due to inverting. Okay, next we have okay, so just a recap. Okay, the V out due to non-inverting is this one. Okay, 1 plus RF over R1 times R3 plus over R3 plus R2 times V2. And then the V out due to inverting is just simply equal to negative RF over R1 times V1. And the total output would be a combination of V out due to non-inverting and inverting inputs. Okay, so meaning we'll just simply combine the equation number 3 and 4. Okay, so combining equation 3 and 4. Okay, so we're just simply combining equation 3 and 4. Okay. Okay. So equation 3, so this one, okay, we just copy. Then plus, copy, okay, okay, plus negative RF over R1 times V1. Okay. If all resistors are equal, so we have R1 is equal to R2 is equal to R3 is equal to RF is equal to R, then, okay, so 1 plus RF over R1, so would be just equal to 1 times R over, okay, 2R, okay, times V2 plus negative RF over R1 is just simply equal to 1. So it would become negative V1 here. So 1 plus 1 is 2 times 1 half V2 plus negative 1 V1. So therefore, we have the total would be equal to V2 minus V1. Okay? So if all resistances are equal, so the total V out would just simply equal to V2 minus V1. So this differential amplifier is also called as unity gain analog subtractor. Okay? So again, the equation only works if all resistances are equal. So we just simply equal to V2 minus V1. Okay? Then we have, okay, so this will be your quiz. Okay, let's proceed now the instrumentation amplifier. So instrumentation amplifier actually consists of 1, 2, 3, 4, 5, 6 resistances plus RD. So essentially 7 resistances. So the R1 to R6 usually they have equal values, okay, whereas RD sets the gain. So it is RD that usually sets the gain. So instrumentation amplifiers provides the highest gain. So take note, we have a gain of 1 plus 2 R1 over RD. Okay, 1 plus 2 R1 over RD. Then you have V2 minus V1. So we have instrumentation amplifiers often used in sensors, sensing very small signals. So let's say in terms of millivolts, okay, to greatly amplify the signals. Okay, so the desired signals is usually in differential form. Okay, so when you say differential form, if this is V2 is positive, V1 is negative. Okay, so you'll have a great amplification. Okay, common mode signals are usually greatly attenuated. So generally should be cancelled or nulled, okay, or greatly attenuated. Because common mode signals, so when you say common mode signals, so if V1 and V2 both receives the same signal, same amplitude, same phase. So that is common mode signals. And common mode signals are generally noise. Okay, so that's why it should be greatly attenuated, whereas differential signals are desired signals and should be greatly amplified. Okay, so if you're going to notice, so R3, R4, R5, R6 is actually a differential amplifier. Okay, so we have a differential amplifier here. Okay. So we start with R1 and R2 here. Okay, so we have 3 op amps. So 1, 2, 3. Okay, so let's start the analysis. Okay. Okay, V out. So we have, okay, op amp number 1 also have a V out due to inverting input. Okay, so how? So we have here, we have what we call a virtual ground. So when you say virtual ground, these points, this point and this point, it appears as if they are connected, although they are not. Okay, that's why it's called virtual ground. So if you're going to have this circuit in a breadboard, then you try to measure these points and these points, it would exhibit same values. Okay. So therefore, if this is V2, this is also equal to V2. Okay. So the equation for inverting op amp is negative RF over RI times the input voltage here. So again, our RF for op amp number 1 is R1 and our RI is RD, such that we have this equation V out due to inverting is negative R1 over RD times V2. Okay. So therefore, the output for V out 1 is the combination of V out due to non-inverting and inverting. Okay. So simply put, we just simply combined equation 1 and 2. Okay. So combine equation 1 and 2. So we have V out 1 is 1 plus R1 over RD times V1 plus negative R1 over RD V2. Okay. So, okay. Or, okay. Or simply put 1 plus R1 over RD V1 minus R1 over RD V2. Okay. So this will be our equation number 3. Okay. We have, okay, so this time we have op analysis for op amp number 2. So again, we start with the non-inverting input, so V2. So what is the output due to non-inverting? So again, 1 plus RF over RI times input voltage. So our RF for op amp number 2 is actually R2. So this is our feedback resistor. Okay, R2, and our input resistor is RD. Okay, so we have 1 plus RF over 1 plus, so therefore the output due to non-inverting input for op amp number 2 is 1 plus R2 over RD times V2. Okay, but op amp number 2 also has an input to the inverting due to the virtual ground. Okay, so virtual ground, so again this point and this point have the same values. So therefore, if you have an input here, so you have an input at the inverting here, so we can have this formula, negative R2 over RD times V1. Okay, combining two V outs for op amp number 2, so combining positive. Okay. Op-amp number 2 also has an output due to inverting input. So again, so this is a virtual ground. So if this is V1, this is also equal to V1. Okay. So we have negative R2 over RD times V1. So to determine the output for op-amp number 2, so we just simply combined equation 4 and 5. So combining equation 4 and 5, so we have V out 2 is 1 plus R2 over RdV2 plus negative R2 over RdV1. Okay. Or simply put, okay, so we have 1 plus R2 over RdV2 minus R2 over RdV1. So that's our equation number 6. Okay, so for op-amp number 3, okay, again, so this R3, R4, R5, R6 is in fact a differential amplifier. Okay, so a differential amplifier, if R3, R4, R5, R6 are all equal, then V out 3 is just simply equal to V out 2 minus V out 1. So take note that the output for op-amp number 2 is 1 plus R2 over RD times V2 minus R2 over RD times V1. And the output for op-amp number 1 is 1 plus R1 over RD times V1 minus R1 plus over RD times V2. Okay. So following the equation here, okay, V out 2 minus V out 1. So we have this one, we just simply copy this one minus this one, such that we have this. Okay. Okay, so if R1 is equal to R2, so if R1 is also equal to R2, then, so let's replace R2 with R1, or vice versa, so whatever suits you. So we have 1 plus R1 over RdV2 minus R1 over RdV1 minus 1 over R1, 1 plus R1 over RdV1 minus R1 over RdV2. Okay? Okay, so we're going to transfer the R1 over RdV2 here. Okay? We'll combine it with this term. Okay, so take note that this is negative R1 over RD preceded by another negative. So negative, negative, so it's actually a positive. Okay, so that's why if we're going to combine the this term here, so it becomes plus R1 over RD V2. So that's why this becomes plus 2R1 over RD V2. Okay. Likewise, if we're going to combine the negative R1 over RD V1 to the V1 here, preceded by to the V1 here. Okay. Okay. To 1 plus R1 over RD times V1. Okay, so take note, this is negative and this is preceded by negative. So if we're going to transfer this term preceded by negative, so it becomes positive. So that's why we have 1 plus 2R1 over RD times V1. Okay? And then factor out the 1 plus 2R1 over RD term. Factoring out 1 plus 2R1 over RD term times V2 minus V1. So this is now the V out for op-amp number 3. So take note that your gain is 1 plus 2R1 over RD. Okay, so instrumentation amplifier provides the highest gain of all the amplifier op-amp circuits. Okay, so that's it. Okay, so you have assignments. So we have differential amplifier, this one and this one. Okay, so that's all for now. So I'm still coughing, so please pardon me. Okay, so bye.